Hi, my name is Stanley, and we are presenting the High Performance Cooling Garment. Up here at the top, you can see the names of my fellow team members, our advisor, and our sponsor. We will now go through each part of our poster. Our project was created to help people lower their core body temperature quickly and non-invasively, particularly individuals working in hot environments. The device contains a cooling sleeve and backpack encasing the electronics. We created a closed loop using a small pump and reservoir to pump the water through a manifold that splits one large tube of coolant into several smaller tubes to increase the surface area as the tubes conduct heat away from the vasculature of the forearm. This water is then put through another manifold to flow past the thermoelectric coolers to have the heat obtained from the body removed.
In order to design an adequate and successful cooling garment, we outline the following objectives. The unit must be self-contained and portable, which means that it must be able to run on a battery or charging. The garment itself will be fitted to the forearm per request of our sponsor due to accessibility and wearability. It will need to incorporate thermoelectric coolers as the main source of cooling. And last but not least, it must be designed to comfortably fit an array of individuals by means of adjustability. The following metrics were also taken into account that line up with our objectives. Since human skin is already heat regulating, cooling calculations were simplified in order to come up with a rough estimate of heat loss. By simplifying the forearm into a radial resistance network, the following target for the cooling the body was calculated. In order to continually remove heat from the body in ambient air, 20 degrees Celsius, the TECs would ideally pull 150 watts of heat from the body. In experiment, we were able to run the TECs at 16 degrees Celsius, which removed 100 watts. In order for the device to be portable, we constrained our design to 15 pounds. To achieve a long-lasting charge, we decided the target design would last up to 2 hours, given that the longest it may be on a single individual, it may be approximately 30 minutes. We were able to achieve half of this goal. The device can last up to an hour without needing to recharge. Lastly, to keep costs low and competitive, we constrained ourselves to $1,000. Thinking this would be an overestimate. In the end, our device turned out to cost a total of $1,000 for hard goods and componentry.
For our garment, we needed to maximize the number of tubes in order to maximize the surface area that the coolant could come in contact with the skin. In order to do that, we used these red TPU filament 3D printed pieces, and those are where the tubes can just snap into and keep everything equidistant. Those were attached to a thick cotton filament, and that was in order to give the garment some structure. And you can see that in the picture on the right. In the picture on the left, you can see that that cotton garment was then sewed into a canvas outer where we could attach grommets and then weave through an elastic piece so that all you had to do when you put on the garment is pull the elastic and it would tighten to many different sizes of forearm.
For the cooling system itself, it was comprised of 5 different parts mounted to a backpack. In the top left, number 1 is the electronics, which is a custom PCB with some power electronics to control the TECs as well as the pump. And then also it can take measurements of the temperature of the person and the temperature of the coolant. Number 2 in the top right is the pump and reservoir. They were originally for PC water cooling and then mounted via a little 3D printed bracket to the backpack. Number 3 in the middle is the large CPU heat sinks with the fans on them. Underneath those are the TECs themselves, and underneath those are some water blocks which remove heat from the coolant and deliver the coolant back to the pump or to the garment. Number 4 in the bottom left is the power source, which are 2 4S lithium polymer batteries. Normally those are attached to the belt of the backpack, but they're shown here for visibility. And the number 5 on the right side is the manifolds that split the main coolant hoses into the many small hoses that were shown earlier.
So the human body is a very difficult thermal system to measure. So in order to quantify how much heat our device could pull away from the body, we designed an experiment around an isothermal skin temperature electric calorimeter. In that experiment, the garment was completely submerged and allowed to run for the duration of the charge. And the power required to maintain the calorimeter at body temperature was equal to the amount of heat removed, which was an average of 92 watts with a peak power of 110 watts. This result ignores vasoconstrictive effects, but is a good approximation of the electronics when combined with a maximally sized garment.
Our next set of tests were human trials so that we could measure our main objective, which was global versus local cooling effects. First, we had our subjects raise their core body temperature by 2 degrees. In our control experiment, our subjects simply cooled down naturally. But in our experimental trial, we had our subject cool down with the aid of the garment. You can see this control image versus experimental image on the bottom, on the left side being the control and the right side being with the aid of the garment. On top, you can see an image of 2 forearms. The one on the left is the before image where the garment has yet to be applied, and on the right is the after image when the garment has been applied for approximately our measured cool down time of 15 minutes. Clearly, there are differences in the local cooling and somewhat of a difference in the global cooling with maybe some minor vasculature reduction. But in general, we did not achieve our global cooling objective to the extent that we wanted to.
In conclusion, we were able to successfully build an electronic cooling device that utilizes thermoelectric coolers and is capable of extracting 92 watts of heat on average from the body. Because of some limitations in resources and the difficulty in accurately measuring human core body temperature, we could not analytically conclude the effectiveness of the device in globally cooling a body. But that being said, the results of the thermal imaging and the calorimeter experiment provide compelling evidence that our device removes heat from the body locally very well. In order to achieve global cooling, we can design other garment iterations that target a larger part of the body, such as the chest. Because the garment and the cooling system of our design are independent from one another, our device has modularity that can accommodate many different garment iterations in the future. Now we will show a video of our device in action.